So introduction to timers. A timer or counter is like a clock and can be used to measure time events. The timer can be programmed by some special registers. The controller of the Arduino is the Atmega 328, which has three timers called timer 0, timer 1 and timer 2. And if you look at the diagram, the timer counter input output pins has been shown over here. Timer 0 and timer 2 are 8-bit timers, whereas timer 1 is a 16-bit timer. The most important difference between 8-bit and 16-bit timer is the timer resolution. With 8-bit timer, how many number you can count? 2 to the 8, 256. With 16-bit timer, how many number you can count? 65,536. Okay. So 8-bit timer is capable of counting 2 to the 8, that means 256 steps from 0 to 255. 16-bit timer is capable of counting 2 to the 16 equal to 65,536 steps from 0 to 65,535. So what is the usefulness of timer? Timer is an important concept in the field of electronics. Every electronic component of a sequential logic circuit works on time base to keep all the work synchronized. Okay. An advantage of the timer is that it is totally independent of the CPU. Okay. Thus, it runs parallel to the CPU and there is no CPU intervention, which makes the timer quite accurate. This is why using a timer is preferred for long delays instead of simply using the delay function. Okay, because timer works independently of the CPU. The drawback of delay is that your loop gets halted and functions above and below the delay are not being executed during the interval. So we can overcome this disadvantage by using timer. A timer approach is a little harder to implement, but the main loop keeps executing and only excludes the code and functions which a programmer wants to exclude. Okay. If the programmer needs multiple tasks to occur at the same time, or if the programmer's application requires that you constantly read or save data from inputs, using the delay function should be avoided. Okay. So these are the timer basic, how it works. Look at over here. Due to this counting feature, timers are also known as counters. Once they reach their maximum possible value, the program does not stop executing and the timer count simply returns to its initial value of 0. In such a situation, we say that the timer counter overflows. Look at the picture. Starting point 0, beginning. Okay. Then it count 1, 2, 3, 4 up to 255 for 8-bit counter. Okay. When it reaches at the top, counts till top, then it overflows. When it overflows, it go back to 0. Again, start counting. So with 8-bit timer, you can count up to 256 steps or pulse.
So, sir, then we can say it's work like a loop.
Yes.
Or
yes. But the main advantage, main beauty of it, okay, what is the main beauty? That means the main clock frequency is 16 megahertz. Okay. So if you use a pre-scale, what happens? That means you divide the main frequency by a number. Then it reduces the frequency. When it reduces the frequency, it increases the time clock cycle. That means time is same, but you are reducing the frequency. That then each clock cycle take more time. So in this case, if you use 256 count, and each clock will take more time, then more time you can count. That is not possible with the main timer. That means in main timer it will overflow many times in a second. It is not possible. Okay, so you need to keep track. When it overflow, okay, one count, another overflow, another count. Okay, so this is the one way, overflow. Overflow is one technique that you keep track of the counting. When there is an overflow, it set a bit in the flag register. So you check the bit. Okay, there is an overflow, one count, another overflow, another count. Okay, so it is easier. Just check a single bit and you know how many count has been made. This is one technique of counting. Okay, that means you can get different time length because you are changing the cycle time by dividing the main clock frequency with the previous color. Not only you can yes, you can trigger the interrupt from overflow. You can go back. Let's say from any value you can choose in between 0 to 255 maximum value. Okay, and from the, let's say at 100 I will trigger. That means it will count from 0 to 100, then it will again go back to 0. For here, this time I start from 0 and continues till top. Top means the maximum value. It's a maximum. For 8-bit register, maximum value is 255. For 16-bit register, maximum value is 65,535. Okay. So in one technique, how we keep track of how many counting has been made, how many pass, by the overflow. When it go to the max, it will overflow. But this is one way. Overflow by keeping track of overflow. That means when there is an overflow, it will set a bit in the flag register. By checking the bit in the flag register, we know that one count has been met. But this is not the one way. This is not the only way. Another way you can keep track of counting. Let's say when the count value is equal to 100, we reset the counter. Okay, this is another technique. Okay, clear the counter on compare.
Does the carry flag that count goes to 0?
No, you see, this is the register that holds the counting. It starts from 0, 1, 2, 3 up to 255. Again 0, 1, 2, 3 up to 255. So when it goes to the top, you set a bit in the flag register. There's a special flag register, not the main flag register. For the counter, it has its own flag register. Okay, we'll discuss. But so by checking the flag register, we know that one count has been made. So let's say we need for a time span, let's say 30 count. So we can count, let's say 30 times count has been made. So we'll send a interrupts in our trigger for the output pin in the output pin, so that okay, now do your job. Let's say we want a time span, let's say 6 seconds, for example, and for that we need, let's say 90 count. So 90 times we'll check the overflow. We check the bit. Okay, so 90 times has been done. Our time has been fulfilled. So do the job now. So this is the, I think, basic way you can implement timer to make your program more efficient. And this is one way. That means when it goes to the top, it will overflow. This is one technique. Another technique is called clear the counter on compare. In that case, you set a reference value. Okay, you store a reference value. Let's say after let's say 200 count, for example, it will trigger. So it will start counting 0, 1, 2 up to when it will go to 200. Then it will set to bit in a register. By checking those bits, we know that one count has been made. Okay, so clear the counter on compare. After 200 again it will go back to 0. So different way we can do the counting. Okay, and it gives us different time span depending on our requirement. That's our main job. We get different time delay. So we manipulate the timer and we set up how many counts we need to make. So in this tutorial or in this class, we'll go through the basics, plus we'll use a formula to calculate the number of counts we need to make to have a required delay. And which counter will select to get the delay, because different counter give you different time delay. So let's go with all the basics and it will clarify your concept. Okay. For example, timer 0 is an 8-bit timer, meaning that it can count up from 0 to the 8 minus 1 or 255. Once that number is reached, the count resets back to 0 and starts counting again. Okay. How timer works? Timers on the Arduino count up from 0, incrementing with every clock cycle of the oscillating crystal that drives the Arduino. If smaller frequencies are necessary, it is possible to divide the clock through an approach called pre-scaling. Our main clock is 16 megahertz. If we need a smaller clock frequency, then with a factor called pre-scaler, we divide the main frequency. As a result, what we get? As we divide the main frequency, the cycle time of each clock get increased. Okay. So how quickly timer reaches the target count depends on the clock divider. With no divider, the clock would go through 16 million cycles per second and would overflow and resets this counter many times per second. The three timer called timer 0, timer 1 and timer 2 of Atmega 328 can be either operated in normal mode, sometimes called overflow mode, clear the timer and compare, it is called CTC mode, okay, sometimes short we call compare mode, or PWM mode, pass with modulation mode. Okay. For lab experiment 3, we will operate in normal mode using timer 0. Okay. Overflow mode we will use in lab 3. Timer basics, registers. So now we'll investigate the registers that are associated with timer 0. The timer can be programmed by some special registers where we can configure the pre-scaler for the timer or the mode of operation and many other things necessary for proper operation. The registers of interest for our purpose are timer counter register, TC and T0 is the main register that holds the count to store timer count. Timer counter control register, TCCR0A and TCCR0B to define operation mode and pre-scaler. Timer counter interrupt flag register, TIFR0 to observe if there is any overflow. Okay. Output compare register, OCR0A and OCR0B to match the timer count with some custom value. For CTC or PWM mode, we use this output compare register and we don't need this register for the overflow or standard or normal mode of operation. So this is the registers for timer 0. Timer counter control register A, okay, TCCR0A, look at over here, 0 for timer 0, this is the A register and this is 8-bit register. The bits WGM02 that will come from TCCRB register, okay, WGM02, look at over this bit, this bit and this 2 bit. Okay. Decide which mode the timer will run on. Okay, which mode? Okay. The timer counter control register B, TCCR 0B, the 3 clock select bit CS02, CS01, CS00. 3 clock select bit. Look at over here. This is the 3 clock select bit. Okay, what they do? They select the clock source and prescaler value to be used by the timer counter. Look at over here. This is a table. CS02, CS01, CS00. If the combination is 000, no clock source. Okay, if you give 000, timer is stop. No clock source. Okay, timer will stop functioning. If the sequence is 001, no pre-scaling. Timer get the frequency same as the system frequency, 16 megahertz. If the sequence is 010, you divide the main clock frequency by 8. This series bit 0, 1 and 2, CS00, CS01, CS02. Okay, we use this 3 bit to select the clock source and prescaler value to be used by the timer counter. So when those 3 bits are like this, all 0, then no clock source, timer will stop. When these 3 bits are 001, no pre-scaling, that means timer will get the frequency same as the system frequency, 16 megahertz. If it is a 010, then divide the main clock frequency by 8. If it is 011, then divide the main clock frequency by 64. If it is 100, then divide the main clock frequency by 256. 101, divide the main clock frequency by 1024. If it is 110, okay, external clock source on T0 pin. You can use external clock source on T0 pin. Clock on falling edge. If the sequence is 111, then external clock source on T0 pin, clock on rising edge. Very good question. Look at over here. Let's say this is the clock. Okay, this is the rising edge of the clock. Rising edge. So you count when clock is rising from 0 to 1. And what is the falling edge? This is falling edge. So you count when clock goes from high to low. Okay. Timer counter register TC and T0. This is where the 8-bit counter of the timer resides. The value of the counter is stored here and increases or decreases automatically. Data can be both read or written from this register. The register resets to 0 after each overflow. Okay. So this is the register. It holds the count. Timer counter interrupt flag register TIFR0. Look at what there's a bit called TOV0. Timer overflow bit. Timer overflow bit. Okay. How it works? As I have mentioned, when there is an overflow, this bit is set to 1. So your processor check this bit. It is 1. Okay, 1 count. Again it check. Another 1, another count. Okay. So by checking the bit, you know that count has been made. Output compare register OCR0A and OCR0B. Both output compare registers A and B contain 8-bit values that are continuously compared with the counter value. The OCF0A and OCF0B bit in the TIFR register is set to 1 whenever the count matches the stored value. There's a mode called clear the timer on compare. It uses this technique or uses this to register. Look at over here. This is output compare register 0A, and I think this is output compare register 0B. Okay. So you store a value over here. When your count value matches the stored value, then it will reset to 0 and it will set these 2 bits, 1 and 2. These 2 bits are set on from that action. Okay? That there's a count has been made. Most of the registers are very similar to timer 0. Now we are talking about timer 1. We have seen the different registers associated with timer 0. Now we are going to see the registers associated with timer 1, but they are similar. Only change the number 0 for the timer 0, 1 for timer 1, 2 for timer 2. Otherwise, naming convention is same. Same register, same naming convention. Okay.
So can you say all the timers are copies of register, or you can think anything?
Yeah, definitely. Registers helps them to function properly. You see, different activity. We'll see the operation, and you'll see that registers solve different value. Okay, to make it operational. Like your CPU. CPU is the registers and execution unit. So it stores the data, instruction in the registers, and arithmetic logic unit or execution unit process the information. Same thing over here. They help the operation. So this is timer 1. Okay, the timer counter register TCNT1H and TCNT1L. These two register because it is a 16-bit register. Okay, so timer counter register 1H, high order 8-bit it is stored, and TCN timer counter 1L, it is stored the low order 8-bit because it is a 16-bit register and it holds the 16-bit count 0 to 65,535. Okay, so it needs two 8-bit register. In total, 16-bit it needs to hold each count. Okay, high and low value. So this is a timer counter register 1. Other differences include the output compare register are also 16-bit and made up from two 8-bit registers. There is an extra input capture register. Okay, this is another mode of operation. We have seen two modes: regular or overflow mode, simple or overflow mode, normal mode of operation, sometimes it's called overflow. Another mode we have seen, clear the timer on compare mode operation. Another mode you can create. In this case, when you get an interrupt or a special signal from outside from the CPU for other operation, then you read the count sequence, just like a stopwatch. What is the function of a stopwatch? When we stop the watch, we want to see how many count has been made. Same function over here. Suppose for similar activity, a stopwatch activity, when your CPU or other activities send and request or interrupt signal to the timer block, then it saves the time counting in a register. It is called input capture register holds that value. Input capture register holds that value. So this is another mode of operation. Input capture mode. It has a name. Okay, input capture mode. So there is an extra input capture register. There are several extra modes timer 1 can run on. Now we will go through some basic terminology relevant to the timer. Definition of some commonly used terms in timer. One term is called bottom. The counter reaches the bottom when it becomes 0. Look at over here. This 0x. This tells that the value you write over here, they are in hex. Okay. If you write 0b, then It will be only in binary. In binary only you can write 0 and 1. In hex you can write 0 to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. This symbol you can write. Okay? So when you use the term 0x, this is in hex. Now what is max? The counter reaches its maximum when it becomes 0xFF. It is decimal 255 in timer 0 and 0x4F, decimal 65,535 in timer 1. Okay, that's the max value. Okay, now in between bottom and max, we can have other value that we use in CTC mode, compare mode operation, right? So that's called top value. For compare mode, that value we want to compare, that's the top value. So what is the top value? The counter resets the top when it becomes equal to the highest value in the count sequence. The top value can be assigned to be the fixed value, it can be the max value, or value stored in the output compare register A and output compare register B. The assignment is dependent on the mode of operation. So now we'll go to the timer modes. We'll see the normal mode of operation that we'll use in lab 3. The simplest mode of operation is the normal mode. In this mode, the counting direction is always up, incrementing, and no counter clear is performed. Okay? The counter simply overflows when it passes its maximum value and then restarts from 0. No complexity, simple operation. In normal operation, the timer counter overflow flag TOV, timer overflow 0, will be set in the same timer clock cycle as the timer counter 0 becomes 0. That means, since it is something like this, you are counting. You go to the top, then you come back to 0. Again, you go to the top, you come back to 0. So when you come back to 0, then this flag will be set to 1 to indicate that, okay, 1 count has been made. CTC mode. In clear timer on compare mode, the counter is cleared to 0 when the counter value matches either a value stored in OCR output compare register A register. Okay. When the wanted value is reached, a flag in a status register is set to 1. Okay. This method can be more efficient than comparing bytes to detect a match, as checking a single flag is simpler. By checking the flag bit, you can tell, okay, 1 count has been made. It is easier, right? So this is the counter unit. You will get the entire operational view of the counter unit, step by step. So I will go step by step, okay? And each step will tell you what is the sequence of operation. So first step, external clock source. Most commonly it is 16 megahertz for the Arduino. Atmega 328K processor for the Arduino board, 16 megahertz. So this is the clock select H detector. Okay. So over here, whether you supply the original clock frequency or you can use a previous color. So that's, I think, from the step 2. System clock may or may not be prescaled. Okay. Then timer clock is chosen. control logic. Timer clock is chosen depending on the selection over here, either no pre-scaling or pre-scaled. Then every clock period signals the timer to increment or decrement. This is the timer counter. Every clock it signals whether to increment or decrement, 0, 1, 2, 3, like that, okay, or decrement depending on the nature. Finally, after that, sets the timer count to 0 when it goes to the top. It sets the timer counter to 0. No, it initializes before any operation. You must initialize the counter to 0. Okay, so before the operation begins, you initialize the counter to 0 over here. Then chooses between increment and decrement. Signals that timer count has reached the maximum, either top, control logic, or bottom, so that you set the flag bit. Okay, when the timer count has reached maximum, at that time you set the flag bit, interrupt request, timer overflow bit. Okay, flag bit. Signals, if it is bottom, signals the timer count has reached the minimum. From top, it will go to the bottom. Okay, so it will send the at the time it will send the request. Timer counter overflow flag set when timer overflows goes beyond maximum value. Okay, so we have seen the entire operation step by step, how it set the flag bit. Okay, any question on the previous picture? Have you understood the entire operation?
The timer minimum এটা বলতে 0 hours থেকে যেটা বলতাম
Look at over here.
3 AM
3 and 3B. Okay. Signals that timer count has reached maximum. Look at over here. It is like this. Counting, going top. Okay. So when it comes to top, it's signal. Okay. It has gone to top. Then it will go to 0. It will decrement. Sorry, from top it will go directly to 0. Okay. So when it goes to 0, look at over here. When it goes to 0, signals the timer count has reached minimum. At that time, when it goes to 0, timer counter overflow flag set when timer overflows. That means at this point it overflows. When it overflows, come to 0, the flag bit is set. When the flag bit is set, then your CPU can take necessary action. This is the output compare unit in CTC mode. In CTC mode, we use this output compare unit. Okay, what we do the output compare? Look at over here. Output compare register A, output compare register B. This is the comparator. Okay, so this it can be 8-bit value or 16-bit value depending on the number. Okay, so entire value will get compared with the present count of the timer. If there is a match, what will happen? If there is a match, that means if there is a match, then it will set this flag bit. It will set this flag bit. Output compare flag bit A, output compare flag bit B. Okay, so when it set the flag bit, then it can take necessary action depending on the requirement. Depends on the program. Okay, what of? Because you know this is the right time. Now do your own job. What you would like to do. Okay. So this is the output compare unit, and if you look at the color, red color signals entering and exiting a block, normal mode operation. Blue color signals entering and exiting a block for CTC PWM mode, and green color description of a block. So any question over here? Also, it has given the sequence. 1A, 1 is the current timer count. Then 2A is the count stored in OCR NA. 2B is the count stored in OCR NB. Then 3 is the send signal. Okay, in input if inputs are equal. Okay, 3B send signals if inputs are equal. Okay, there is two mode. Okay, in one is the overflow mode, another is the delay timer on compare mode. Okay, then count stored in output compare register. Okay, and you compare fixed stop value. So 6 mode, you give the fixed stop value, then you compare over here. Maximum timer value chosen, then signals the timer count has reached maximum. Okay, then signals that the timer count has reached my minimum. Then you set the flag bit. Okay, output compare flag bit interrupt generated if enabled. Output compare flag bit A and flag bit B. Okay, so output compare flag set interrupt generated if enabled. Okay, finally generate a PWM or variable frequency out on this pin. This is the same picture in bigger form. Okay, same picture in bigger form. Now we are going to our main point where we are going to implement this by ourselves in our lab. So before we implement it, we need to learn some formula that will make our life easier. So we'll grab the formula over here. Okay. So let's see step by step. Timer for delay. Calculating count. Timer needs a clock pulse for each transition from one number to the next. So we want to establish a formula relating the necessary timer count for a specific delay with the timer clock period frequency. For CPU frequency 16 MHz, system clock period is 1 divided by 16 m. 16 mega. 1 divided by 16 into 10 to the power minus 10 to the power 6, right? So if you have a calculator, you can check it. It becomes 62.5 nanosecond. Each clock takes 62.5 nanosecond. So if timer clock is same as the system clock, it takes only 62.5 nanosecond for every transition from 0 to 1, 1 to 2, 2 to 3, so on. For every transition, it takes 62.5 nanosecond. So what is the problem over here? Okay. The problem over here, suppose with 62.5 nanosecond for every clock, right? Every count. So for 8-bit timer, how many count over there? 0 to 250, 256. So you can multiply 256 into 6.5 nanosecond. A small value will get. Suppose you want to count larger value. Then if you use this frequency, clock period 62.5 with 256 count, you cannot count larger value. But the technique is like that. If you increase the time cycle by dividing the main clock frequency, if you divide the main clock frequency by the prescaler, you increase the cycle time. As you increase the cycle time, then you can imagine this. If you 8-bit counter, then within 256 count multiplied by the larger cycle time, timer span will get increased. So that's the technique. That's the main technique. We want to count different range of timing by using different prescaler value. Okay. So let's go with it. Let's grab a formula first. Okay. We can see that 3 time period over here. Look at over here. Count 0, count 1, and count 2. 3 time period are needed to count 2. 0, 1, 2. So timer count equal to number of periods needed to reach the count minus 1. Yes. So to count 2, we need 3 clock cycle. So how many timer count? We get number of periods needed to reach the timer count minus 1. And we want to reach this value 187.5. Okay, divided by 62.5 minus 1. So timer count is 2. We have counted 2. Okay, that's the formula. Also, we can see that to get a delay of 187.5 nanosecond, we need 3 periods lasting 62.5 nanosecond. So the number of periods needed equal to required delay divided by timer clock period. So number of period needed. Another formula. Number of period needed is equal to required delay. This is the required delay divided by the timer clock period. So two formula we have used over here. Suppose we need a delay of 1 millisecond. To get an idea how long it takes, let's calculate the timer count from the following formula. So how many count it would need to make to get a 1 millisecond delay? So that's the formula. Timer count equal to required delay divided by the timer clock period minus 1. In our last page, we have used the formula, right? Timer count equal to timer required delay divided by the timer clock period minus 1. This is the formula we have used in the last slide. So here required delay is 1 millisecond and timer clock period is 62.5 nanosecond. So timer count, we can use the value required delay is 1 millisecond divided by 62.5 nanosecond minus 1. And if you do the calculation, it becomes 15,999. Now I have a question. Now to get this 1 millisecond delay, we did not use any pre-scaling over here. Normal mode, okay? No pre-scaling. Can you use timer 0 to get this 1 millisecond delay? Can you get from timer 0? Why not? Why not? So what's the problem out there? With 8-bit, how many count you can make? 2 to the power 56. But we need to count 15,999. So not possible. So we cannot use timer 0. We can use timer 1 over here. Very good. So the clock needs to take 15,999 times to give you delay of only 1 millisecond. Maximum possible delay for timer 0 at 16 megahertz is equal to 62.5 nanosecond multiplied by 256. Count 16 microsecond only we get from timer 0. And maximum possible delay from timer 1 at 16 megahertz, you can calculate 62.5 nanosecond multiplied by 65,536, 4.098 millisecond. Okay. So in this case, we can use timer 1 because it can have 4 plus millisecond delay. If we plan to get delay simply by directly counting at system frequency, it is difficult to use an 8-bit timer as it has an upper limit of 255, after which it overflows and resets count to 0. Even with a 60-bit timer, which is capable of counting up to 65,536, it is not possible to get longer delays. Maximum we get 4.096 millisecond, not more than that. So what is the technique? The technique is pre-scaling. By pre-scaling, we increase the cycle time. So each count will have longer delay. Okay. Your activity. For some operation, you need a smart delay. For some operation, you need longer delay. So time is a very important factor. Different job requires different time delay. So different time delay you get by this technique. Yes, kind of a time delay you can use, okay? Depending on your need. Basically, what it does, it increases the cycle time of each count. As it increases the time of each count, overall, with the 256 count, you can count more time. Okay. Similar way with 65,536 count, you can count more. So that's the technique, main technique, right? For pre-scaling. Okay. Look at over here. To stay in the safe mode. Okay. I think. Okay. To stay in the safe side, we use the highest available prescaler and reduce the timer clock frequency to 16 mega divided by 1024. Okay. Because that's the maximum delay you can get. We can use lower value of prescaling depending on your need, but for general practice, let's use the maximum value. We'll go on the safe side, okay? So we divide the main frequency 16 megahertz by the prescaler value, maximum value, prescaler 1024. So we get a frequency 15,625 hertz, not 16 megahertz, okay? So with a new timer clock period, system clock period multiplied by the prescaler, that means 62.5 nanosecond was previous, you multiply by the prescaler, you get 64 microsecond now. Now each count has longer delay. Instead of 62.5 nanosecond, we get 64 microsecond. Okay, longer delay. Now the needed timer count. How many timer count we need? 1 millisecond divided by 64 microsecond minus 1 equal to 15,625, I think, around. It comes. You can use that calculator, okay? There's a decimal point over here. You can use the calculator. So now the timer clock frequency is equal to system clock frequency divided by the prescaler. We can update the equation to the timer count is equal to required delay multiplied by the system clock frequency divided by the prescaler minus 1. So this is the formula that we'll use to calculate the how many count we need for a particular delay. Maximum possible delay for timer 0 at 15,625 Hz, 64 microsecond multiplied by 256. So by using timer 0 now, if we use the prescaler, then we can count 1 millisecond because that's the range now of timer 0. 16.384 millisecond. That's the advantage of using prescaler. Now by using timer 0, we can count up to this delay. 16.384 millisecond. It was not possible without prescaler, right? Now maximum possible delay for timer 1 at 15,625 Hz, 64 microsecond multiplied by the prescaler. Multiplied by this 65 536, not this is not prescaler maximum value. So we get 4.194304 second. Longer delay you can count measure now. By timer 1, we can measure more than 4 seconds now. Okay. Now, if we want to get more delay, so what you do to get longer delays, we'll use timer 1 and add for okay. And for delays longer than 4 seconds, we nested if statements can be used. Okay, nested if statement you can use. Now we'll go for some practice problem. Okay. System clock frequency, what here is 16 megahertz we have used. Okay, 16 megahertz. Yes, 16 megahertz for the Arduino Uno. But we divide this maximum frequency by the prescaler. You get lower frequency but larger cycle time. For each count will have longer delay. Okay. So that's the main technique actually. That's the main technique behind this process. So there's a problem over here. Make and LED blink every 2 milliseconds while using Arduino system frequency 16 megahertz. Using timer to generate the delay without any application of delay function. Okay, so we will not use any delay function. So let's write our program. Over here, delay is 2 milliseconds. Timer 0 can count up to uh, 16 plus millisecond, 60 plus millisecond by using prescaler 1024, right? So timer can be used with prescaler 1024 over here. So number of count needed to reach 2 millisecond is equal to 2 millisecond divided by 64 microsecond minus 1. That's the formula. So 30.25, that means close to 31 count. So 31 count we need to make. Then our job is done. Delay has been done. So that's the program. First, define the pin number that will be used to send the output signal, pin number 8, for example. Integer millisecond. Integer millisecond, that means 2 millisecond we need the delay. Define delay length in millisecond. Then integer prescaler 1024. Define the prescaler. Integer clock frequency. So 16 megahertz divided by the prescaler. Okay. Calculate timer clock frequency. Then float clock period. Clock period should be float. There can be decimal point. So 1 divided by the float clock frequency. Okay. 1 divided by the clock frequency, but the entire field will be in float. Okay. That is fractional part. Calculate timer period. Finally, integer count. How many count we need to make? Equal to millisecond multiplied by 0.001. That means we'll convert it to second. Then divided by the clock period, that is already in second, minus 1. That's the formula. So calculate count for required delay. Okay, this is the defined calculation. Okay, then we go to the main part, setup part. In setup part, we define that pin number 8 that we have used will be the output pin. Okay, now set up the timer over here. Timer counter register TCR 0A initialize with 0 value. Timer counter control register 0B initialize with the prescaler. Setting prescaler for timer clock. And these two value, the WGM 01, 02, okay, this three, I think 3 bit, okay, look at over here. WGM 01 and WGM 00 set to 0 for normal mode. WGM 02 over here set to 0 for normal mode. CS02, CS01, CS00 set to 101. 101 for prescaler 1024. Okay. So we set the normal mode of operation, that is overflow mode, and we set the prescaler 1024. Finally, we initialize the timer counter register 0 to 0 value. Initialize, okay. Then in the loop, you just compare that, okay, have the value inside the counter greater than or equal to the count value. That means how many count? 31. Okay, 31. When there is greater than or equal to 31, then we reset the counter to 0. That means if you draw a picture, 31. After 31 count, we go back to 0. Okay. So we initialize again to 0, go back to 0. Finally, at that time, we do our action. By using the command digital write, at the pin, we can connect a LED. Okay, in your lab, you will connect an LED at the pin, and you will use the command digital read pin used. That means you read the present value and invert it. So if the LED is on, present value will be 1 of the pin. So you invert it 0 and you write 0. So LED will be off. So after 2 milliseconds, that means after 2 milliseconds, you will turn off the LED. And again after 2 milliseconds, if the LED is off, you will turn it on. Because when it is off, this invert will make it high. You send the high value. The LED will be on. So it will blink the LED every 2 milliseconds. Yes? Let's continue. We'll do another example to make a concept more clear. Problem statement 2. Make an LED blink every 2 seconds while using Arduino system frequency 16 MHz, using timer to generate the delay without any application of delay function. Okay, now look at over here. Look at the problem statement. You need 2-second delay. First question come. Which timer you are going to select now? Timer 0 or timer 1? Timer 0 maximum delay you can get 16 millisecond, 16 plus millisecond. And timer 1 can give maximum delay normally more than 4 seconds. If you use the nested loop, you can go more. Okay, so timer 1 should be selected, right?
We can use a nested loop in timer 0.
That will be more complex since you have timer 1 readily available and can easily, without any complexity, you can do. Why you will go for complexity? When you cannot do, that means when your limit get exceeded, then you take extra way. Okay, so we can easily use the timer 1 without any complexity. So we'll choose timer 1. See, look, delay is equal to 2 seconds. So timer 1 can be used with PScaler 1024. Number of count needed to reach 2 seconds. Use the formula 2 seconds divided by 64 microseconds. Keep in mind this is 2 seconds. So bring in same unit minus 1 and we get 31,249 count we need to make. Quite fine with us with timer 1, right? It can count up to 65,535.02. Okay, so timer 1 is quite okay over here. So this is the program for it. Same thing like problem statement 1, only change over here is the define delay length. Delay length all are same. PScaler is 1024, clock frequency 16 MHz divided by the PScaler. Clock period is equal to 1 divided by the clock frequency, and the integer count. This is the formula, same formula, but it will give us the number of count. Okay. So in the setup part again, you initialize the pin for the output, and look at the change over here. Set up the timer. Now we are using timer 1, not timer 0. So you need to initialize. TCCR1A, you initialize with 0. TCCR1B, you initialize with PScaler value. So in this case, what you do basically, you define the mode of operation, that means overflow mode or normal mode, and the PScaler is 1024. So this two line will do the job. Finally, you initialize the timer 1 to 0. Then in the loop, you compare. When the timer 1 exceeds the count value, you initialize timer 1 again to 0 and take the action. You blink the LED. Okay, you toggle the LED output. Okay, in red color it has been mentioned. Okay, same code, only register names have 1 instead of 0 and delay length changed. That's all. Otherwise, similar like program 1. Now, there are some reference you can get.